All right, energy balances. We started to talk about energy balances, and what we have discussed was we did discuss about how we would make a control volume, and the control volume, all it is a closed surface through which we have flows of mass and energy. Very simple concept, very rigorous, very powerful. And we'll see how from there we build to incredible heights. We then talked that the control volume goes one in one. You never have one without the other, and it's an energy balance. And the energy balance was a little bit of a bank account balance, and was what comes in minus what goes out plus what gets generated is what we have. And this balance we have here. In, for example, if it was a bank account, this is your salary. Out would be, if it is a bank account, that's what you spend in rent. QGen is what is generated. That would be like the interest that you gain by having your money in the bank. And all this together is how much money you have in the bank. In the case of heat, heat comes in by convection or conduction or advection or radiation, many mechanisms, or goes out by those mechanisms. And we'll spend the whole class discussing those. And heat can be generated. And there are many physical mechanisms for generating heat. And that can be resistive heating, radioactive decay, can be metabolic heat. And because these heat generations are more associated with different physics, we're not going to dwell into what physics generate this heat or take away this heat, but we will know how to handle them if we were to given an amount of heat that is gained or lost volumetrically. And then the heat stored, and this is like the balance of the account. However, what we saw is that we have some things to think about. And for the heat stored, we said, okay, we use the concept of enthalpy. Enthalpy is the amount of heat mass matters has. So if we take a time 1 and a time 2, the heat stored in this difference during this time is mass times enthalpy. Enthalpy is in joules per kilogram. So mass times enthalpy at time 2 and minus mass times enthalpy at time 1. And this very simple definition got us into the first very non-trivial concept that is overlooked in most textbooks, and it's the concept of advection. In advection, we're transferring heat, but not by getting things hotter in temperature, but by transferring mass that brings thermal energy. And then we showed how if we consider a system, here we have a control volume, and here we are adding an amount of mass delta M. And interestingly enough, the mass M is at a given temperature with a given enthalpy, right? And enthalpy and temperature go together. We'll discuss this right after this. I add a little bit of mass at the same temperature. So if this was water at 20 degrees, and I add more water at 20 degrees, the final amount of water is at, guess what, 20 degrees. However, we have more thermal energy than before because we have more mass. And this is very important. Sounds like a silly thing to say, but this is the foundation of the calculation of heat exchangers. And this is the foundation of calculating systems into which we can have evaporation, condensation, and lots of complexities about mass flows. So in this case, the heat of advection is the enthalpy it has by the amount of mass that came. And we're going to see that soon how we use this equation and we build into something that is going to be the foundation of heat exchangers. And those of you in chemistry will be using heat exchanger very much for your design project. But even those of you in MATI, for example, when you're welding, that is my specialty, and you're feeding a wire into the weld, the wire comes at a given temperature and goes into the weld at a different temperature because it melts and evaporates. And this equation is crucial. Then we stop the class just as we were saying, okay, there is a relationship between temperature and enthalpy. I just mentioned they go one in one, and we looked at this graph. In the horizontal axis of this graph, we have temperature. Can be, if this we have here was water at atmospheric pressure, this would be 0 degrees, this would be 100 degrees up here. The vertical axis is enthalpy, is the amount of heat this water would have. And what do we see? We see, let's talk about water in liquid state. That is the one we're most familiar with. So what we see between 0 degrees and 100 degrees, what we see is that as we increase the temperature, we increase the amount of heat content. Of course, higher temperature, more heat. That makes sense, nobody doubts. What is the relationship between how much more heat do I gain for a given amount of temperature? This is the concept of specific heat, which we discussed. And I mentioned that because we're not gonna use in this class systems in which the thermal energy creates mechanical work, CP and CV are going to be essentially the same for us, and we're going to call them C. Typically, what we care about is CP. But if the systems don't do mechanical work by expansion, for example, like a Carnot engine, we don't need to worry. And this C is the variation of enthalpy with temperature, and it's a derivative. So very, very important, and you will be asked this, I believe, as we have to do the quizzes online, but every year I would ask for that. And what is that? The specific heat of liquid water is the slope of this line. That's what the specific heat of water is, the slope of this line here. Now, there is something interesting which you already know, but I want to put together because you know some things from your intuition, and it's essentially you keep your intuition, it's very important. And you know some things because you have studied them before, but often your intuition and the formality of what you have learned, something they have not connected, but in this class, we will connect it. So we just mentioned that, yeah, something that has higher temperature has more heat. And that means the derivative of enthalpy with temperature is the exact, very rigorous metric for that. But we have more things. So we all know that if water gets too hot, it's going to evaporate, or if it gets too cold, it's going to freeze into an ice block. And we also know, because you have heard the term latent heat, and what that latent heat means is an amount of heat that is associated with a change of phase. For example, in the case of liquid water, to turn from liquid water into vapor, we need to break the bonds that kept the water in the liquid form and turn it into molecules that are flying around. That energy to break those bonds, that's what we call the latent heat. And if it is pure water and it's at atmospheric pressure, we can have liquid water at 100 degrees, or we can have vapor at 100 degrees, right? So temperature alone is not enough to tell us how much heat we have. Just infinitesimal before 100 degrees, we have the amount of energy. Let's make a mark here. We would have this amount of entropy. Oops. Okay, that gets interesting. Okay, what? Oh God. Okay, let's see. No. All right, live and learn. So we were talking just before 100 degrees. This would be the amount of enthalpy, and the total amount of thermal energy would be mass times this enthalpy. And right after 100 degrees at atmospheric pressure, we would have this other amount of energy that is much higher. And it all happened at 100 degrees. And if the water was not pure, or in the case of people in materials, that we care about materials that would be alloys, in that case, we would have like a narrow range of temperatures in which things happen, right? It's a narrow range, and they are associated with this latent heat. The same if we are too cold. Now, as the water molecules have less oscillation and start to get into a crystalline structure that would be that of ice, they would absorb a lot of energy, and this would be all at 0 degrees and would be given by this latent heat. You know this intuitively. You have seen some of this formalism before, but now we're going to put this into numbers. So okay. Okay. Okay, good. So we already discussed this about latent heat. Something interesting, I already mentioned that the book uses H, but we don't use H, we use I because H we'll reserve that for some other concept. But something else, and I'm staying with the notation of the book I recommended, is they call the solid state, they use a subscript of S. Here, the liquid, the gas state, they use a subscript of G. But for the liquid, for reasons I don't understand, and I believe I will change in future classes, but I haven't yet. For liquid, they use a subscript F. For fluid, maybe, I don't know. But ISF will be the enthalpy of solidification, and IFG will be the enthalpy, the latent heat of evaporation. So I will do an example with you. Let's see how this goes. So the example is, let's, oh, I don't like this. Why? Okay. Let's see. Okay, fine. Calculate heat, and it's in your notes, to melt 1 kilogram of ice at minus 20 degrees C into water at 20 degrees C. Right, and this is something we know all too well because our winters are minus 20, all right. And often we walk in and our boots are full of ice that used to be at minus 20. Now it becomes 20 when we're inside the house and it's water and it makes a big messy puddle. So how much heat is needed to melt ice? This is a trivial question, but we're going to do it formally to see how these equations work. And the good news is that these very powerful equations eventually help us to solve very, very complex problems. So, okay, so step number one. Step number one is control volume. And because nobody's saying what shape it has, so typically when we don't know the shape of something, we draw our potato. And I'm going to this potato is the water or the ice. And the control volume indicates that it's inside. So this is ice. And that's it. So let's do step number two. Step number two is to do the energy balance. So we never do one without doing the other. If you're going to do one, you do the other two, right? The energy balance. And the energy balance, I'm going to write it here on the side. So before I change this view. So the energy balance is Q in minus Q out plus Q generated equals Q stored. This is the most important equation of the whole class. You're going to see hundreds of equations. You don't need to memorize them, not even if the class was in presence, because there will be equations to calculate things like the cooling of water going inside a tube of triangular shape. We have equations for those. You're going to learn them. But all of those trace back to this equation of in and out minus out plus generated equals stored. So in this case, Q in is the heat that goes across the control volume. Q out is what would go out. Q generated is whatever would be generated inside, Q generated. And Q stored is the balance of all these things, right? So let's do something. In this problem, much like in many others, the information is not much like many others. Life is this way. You never have complete information. So, for example, I only said we have a chunk of ice that we're melting. I didn't give a geometry, so I drew a potato. But that's fine. Also, I didn't say all the details about this block of ice. I didn't say if it was radioactive or not. So let's say it's not radioactive and we are not generating any heat inside this control volume. So this term, I'm going to take out. No Q generated. Now, if we're talking about radioactive ice, this amazing equation can account for that. not today. Something else. To melt the ice, we need to put heat in. But at the same time, some of the heat might be being lost. I don't know. I didn't tell you that this block of ice is losing heat by radiation to the outside or things like those. But because we're talking about the energy we need to add to melt the ice, and nobody says anything about heat losses, I'm going to assume no heat out. On your exam, I'm going to tell you what to assume or not. And if I don't tell you, you'll assume things that are reasonable. Now, the interesting thing of this equation that now we ended up with this equation now became the heat we needed to give to melt the ice equals Q stored. Sounds like obvious, but it's not. It might have not have been if the ice was radioactive or we have some weird mechanism of heat loss. All right, so to answer this question, the question was, how much heat do we need to put? How much heat goes in? And we said the heat that goes in is the heat that is stored. So now it gets interesting because we need to see what the energy stored is. So Q stored was M2I2 minus M1I1. Too bad this class is not in person because these problems are so much better to be done talking. But if you have access to your chat, I would like to ask very, very briefly, very quickly, a very simple question, and is, are M2 and M1 different? Is M2 bigger, smaller, or the same as M1? I'd like to hear, I'm watching the chat, and I'd like to hear what you think. Thank you. This is amazing. So many of you said same, and same is the official answer. So I'm going to say this equals mass times I2 minus I1. Now, just to emphasize again the power, the amazing power of this equation, what you said is something I agree with. But now, if I were to say, is it exactly the same? The answer is no. The answer is not exactly the same because some of the water is going to evaporate. Even if it is below boiling point, there is still vapor pressure. So actually, M2 is a little bit less than M1, right? Because a little bit evaporated. Of course, it's so little, we're not going to worry about it now. Something you're going to learn in this class is that good engineering is the art of the good lie. So M2 is a little bit less than M1. In this case, the difference is so small that it doesn't matter. So we're going to say that M2 equals M1 and our life is going to be a lot easier. Is it true? No, it's not true. Does the difference matter? No, it doesn't matter at all in this case. So we're going to say one thing, knowing it's not exactly true, but it's more or less true, and it's going to make our life so much better, right? So amazing. I love this class because some things that are so simple help us think about problems that are so much more difficult. To give you an idea, in welding, instead of melting ice, we melt steel. And you know what? When you melt the steel evaporates and turns into fumes that are bad for the welders. And in that case, the difference between how much electrode you melted and how much it went into the lungs of the welders is a difference that matters a lot. So in that case, we do use the evaporation term. Not here, not today. We will have a unit on evaporation later on in the class. Okay, so I2 minus I1. So the mass we knew is 1 kilogram. So the real question is, what is I2 minus I1? And I'm gonna change the page again here. So I2 minus I1. And here we have temperature, let's say in degrees C. And here we have enthalpy in joules per kilogram. And here, let's the curve is going to say we are at 0 degrees here. We started at minus 20 degrees C. Actually, I don't need this degree C because it's in the axis. Oh, what happened here? Okay. If I lost the whiteboard, please let me know. Here we are at 20 degrees C. And what would be? The ice was at 20 degrees and I need to add heat. And as I increase the temperature of the ice, it gets hotter and hotter and hotter. And when I reach 0 degrees, I need to keep putting heat. And this heat goes only into melting the ice. If we were to put a thermocouple or a thermometer or an infrared parameter, we would measure 0, dead on. And the thing is melting, it's absorbing heat. And the temperature says, no, I don't see any change in temperature. But because you took the heat transfer class, you know, aha, yes, I didn't change the temperature, but that does not mean I didn't put heat, because I put heat. I'm putting a lot of heat. And then I melted everything again. And I keep increasing the temperature. So this will be, let's call this T1. Let's call this T2. And okay. What is the name of what should I call this magnitude there? You can put it on the chat. This could be done. What should I call this? Thank you. I1, and obviously this would be then I2. Cool, cool. So now I need to calculate I2 minus I1. Very simple, but only simple after we have thought about it. So we're gonna think about it. And because it's these things can trip us up. So I2 minus I1, and this is the way we're gonna go. What do we know? What do we know? Let me make a mark the things we know. We know, because it's tabulated, we know the specific heat of ice, right? If this is 1, this is specific heat of ice that is solid. We also know, if you get the book, as I'm very strongly suggesting you do, you're gonna see at the back of the book, it has tables upon tables of thermal properties of materials, including water, air, steel, ceramics, insulation materials, everything you want. Here, what should I call this one? If this is 1, what would this be? CF, thank you so much. You guys are super awesome. Who said online teaching is not good? We're doing super well. All right. All right. So I know that, let's make a note here. This is, let's call it solid at melting, and let's call this IF at melting, right? So I know this I1 because it's tabulated. Then sorry, I know this one is okay. Let's do this. I2 minus I1. Oh, very interesting here. Okay, whatever. So we want okay, I2 minus I1. And I can say this would be I2 minus IF IFM, right? That it would be this part here plus IFM minus ISM. This is this other part here plus ISM minus I 1. All right. Would you agree with me on this? Right? This is this third part here. I don't see you guys, but it's okay. I'm going to assume all of you are nodding, saying yes, yes, yes. So this is important. As you realize, if I wanted, I can go and say, oh, IFM with a minus and one with a positive, and here is ISM with a minus and here with a positive, and this is true. But why did I make it more long, perhaps more difficult? No, of course not. It's not to make it more difficult. Let's start with something easy. IFM minus ISM. Let's say I'm going to erase this part here. So if I get IFM minus ISM, what do you call that? I'd like somebody to put on the chat what we should call this. Super awesome. Thank you. Thank you. Exactly. This is ISF. That is latent heat written in the particular language of heat transfer, right? We say latent heat or heat of melting. This is the words, but yeah, because we're going to be using it in formulas, we have to give it a name. Ends up looking like Egyptian, right? But that's okay. As long as we know Egyptian, then we can build pyramids. We're going to build amazing pyramids. So, okay, so this part we know now. Because we did this trick, we know this part. Let's see, I2 minus, let's do this. Let's do I1 minus, let's do this part here, ISM minus I1, IS and melting minus I1. And let's call this guy here Tm because it's a melting temperature. Does anybody have an idea of how to write this using tabulated data? All right. So we can use here the concept of specific heat. So if we assume that this slope is constant, which again, is it constant? No. Is it more or less constant? Yes, it's so close to constant that really it's not worth getting into the pain of doing the integral. Sometimes yes, not for the case of water. And as we're starting to learn this part of the class, let's take it easy. So we're gonna say this difference is specific heat of the solid. This is a small c. I'm not doing it too well. You're gonna see that the big C means something else, but it's a small c times the difference between Tm minus T1. Why is that? Because that's the definition of the slope. If you want, you can see it this other way too. I'm going to do exactly the same, but from I'm gonna get the same to the same point, but we said CS is dt is di with respect of temperature. That would be, in this case, if we say is a constant slope, would be ISM minus I1 divided Tm minus T1. I hope this makes it clear. These two equations, you realize, are the same. Now, I have been going very slowly on something that is quite simple, but let's put it all together. And you see how in this heat transfer class, we take these tiny steps that each of them are obvious, but the end result is far from obvious. This is the difference between technologists or good, hands-on people, that they can do many things. Maybe we cannot do them, but when the things start becoming complex, we exceed our ability to have intuition. It's not going to be your problem because you're building this rigorous way. So I'm going to write now I2 minus I1 would be I2 minus I1 f this minus this, that you would, by now you know that this would be CF, small c, CF times T2 minus Tm plus ISF plus C solid times Tm minus T1. All right. This is not a formula to memorize or anything, but this is so you see how we built from little steps, from very small concepts into this formula that is not intuitive, not at least on first sight. So, and if we multiply this by the mass, we would get the amount of heat we needed. So the straight answer to this is in this page here, and where we did, this is the same formula we just saw. We multiply by the mass, that is a kilogram, and gives us 458.3 kilojoules, right? Nothing here was really new to you. You knew the concept of latent heat. you knew the concept of specific heat. You knew that ice melts, but we put it all together and we're able to put a number into this equation that is an everyday equation for us in the winter. So it's all in the notes. Please take a look, because there are a few more things in the notes that I discussed here, like details about significant digits. Okay. Okay. Okay, good. So in the case in which we have a specific heat is not constant and you need to account for this variability, here I have a worked out example. I'm not going to do it in class because we don't have the time, but it's here worked into the smallest detail. Please take a look. And here we have an example that I typically like to do in class, but as we are learning to do things in virtually, please take a look at this example, which is super trivial. I typically set aside 5 minutes for us to do it in class, and I was planning to do breakout rooms. We're running out of time. So it's here, worked in all the details. And the question is, okay, let's forget about melting or phase changes. If we make pasta and we fill up a pan with 4 liters of water, that is more or less what it takes. And we increase the temperature from 0 degrees, from 20 degrees, let's assume the water is at 20 degrees, to 100 degrees when it starts to boil. How much heat went in there, right? If you're making pasta tonight, you are going to see these in action. And these numbers that are here are pretty much exact. And how would you go about it? Well, you go about it the same way we have discussed. You have to draw a control volume, in this case with the shape of a pan, right? You do an energy balance, heat in minus heat out plus heat generated equals heat stored. And there are questions that appear, right? Do I account for the evaporation of water or not? If I ask you to do it, you have to. If I don't ask you to do it, you might say, I'm going to assume it's small and it's all convenient to me, right? And here's our control volume, and here's the number you would get out of this calculation. Please do it. I was hoping to do it together. There's another concept that I have seen between colleagues that not only have PhDs, but they are professors, and they get confused in the difference between what is heat content and what is temperature. So let me tell you something. Here is something I'm not going to go into detail. I never do, but I wrote it down in properly. 2 things are in thermal equilibrium when they have the same temperature. Now, heat content is a completely different thing. Although heat and temperature go so much hand in hand through the concept of specific heat, we often mix them up. But in this cool example, we show how 2 things can have one higher heat content than the other, but the temperatures can go in different ways, the variations. Take a look, because this shows the case when things are not intuitive. And it's a problem about heating a block of aluminum and a block of steel that have very different specific heats. All right, so in these last few minutes, I wanted to discuss the balance of energy rates. So we discussed how we make a balance between a time 2 and a time 1. That is everything that went in or out or was generated in our control volume. Now, let's say that time 2 and time 1 are very close to each other, right? They are a delta T, right? They're separated by a delta T, and much in an engineering fashion, we're gonna say, let's say that delta T tends to 0. So now we get the deltas become differentials, and the ratios of these deltas become derivatives, right? And this is the balance of energy rates. So you know, this is the exact same equation that we had before for energy balance, except that I divided everything by delta T. Nothing new here, nothing new. I just divided that by delta T, but then I say delta T tends to 0, and this would become now energy rate. And the symbol for energy rate is the small q. So some of you, especially some of you that learn writing in an alphabet without big capitals, big and small letters, right? Upper caps and lower caps. Sometimes it's confusing, but big Q means joules. Small q means joules per second, also known as watts. So so we're going to have a Q in and a Q out, and a Q generation and a Q stored. But in this case, it's always going to be in watts, not anymore in joules. And if we look at the rate of heat stored, right, is much the same as before. If you remember, was delta M2 I2 minus M1 I1. In this case would be delta M times I times per unit time. This equation that looks so simple is ridiculously powerful because we have the M and the I both inside. So we can account for things when M varies, and we can account for the times when I varies. So that's where we're going to pick up on Friday, and we're going to learn many things that are beyond intuition. Let's stop here. Thank you very much. Thank you very much for using the chat. That makes the class a lot better. And if you have thoughts, ideas, or any concern about the class, I'm reading my email, and I'll be on top of all this as much as I can and as fast as I can. Thank you. Let's stop here.